Hey, this is Mr. Mitchell with a video on mixtures. Now, we talked about mixtures before, but we're going to see a little bit more about them in this particular video. We have discussed earlier in the class about heterogeneous mixtures. You may remember that heterogeneous mixtures do not have the same proportions as homogeneous mixtures. If you have a heterogeneous mixture and you take, say, a certain part of it, it may have different proportions than any other part, whereas a homogeneous mixture will have the same identical proportions. And you know, sometimes it's hard to tell whether a mixture is heterogeneous or homogeneous because of well, you can see down here, all of these look kind of homogeneous. I mean, it looks like every part of this is equal to the other parts, but they're actually all heterogeneous mixtures. And I'll tell you what these NM figures mean here in a little bit. Let's talk about several terms that have to do with heterogeneous mixtures. One term that has to do with heterogeneous mixture is suspensions. An example of suspensions has to do with orange juice. Now, a suspension is a mixture that looks uniform when it's stirred or shaken, but it separates into different layers when it's no longer agitated. And that's exactly what happens to orange juice. If you shake it up when you get it out of the refrigerator, it's going to look like this. The top looks like the bottom, and it looks like it's all spread out pretty well. But what happens is whenever it is settled, then these little bitty suspensions start settling in the bottom. All the pulp will settle toward the bottom. If you get it out and drink it without shaking it, you'll have a lot of watery orange juice at the top. So that's what suspensions is. Now, these suspensions are often around 1,000 nanometers in size. Now, mentioning nanometers, that is what these are right here. And you may see that the smaller amount of nanometers it is, I guess you could say the smaller number of particles, smaller size of particles, you might say, the more clear it looks. And I know this is a dark liquid, but you can tell that these liquids are more clear than these soupy looking liquids right here, and much more clear than this soupy looking orange juice right here, if you could call it soupy. Well, anyway, these down here are more like colloids, especially some of the smaller ones here. A colloid, well, particles in colloids are much smaller than those in suspensions, typically about 1 to 100 nanometers. So you can see these bottom three here could be classified as colloids, and maybe even this one right here since it's right at 100. But anyway, some examples of these are Jello, whipped cream, marshmallows, paint, and even blood. Now, in these colloids, the particles tend not to settle down to the bottom. But you can imagine that it looks like it's a homogeneous mixture, but it's just not. If you take one individual part of it, the proportions might not be exactly the same as any other individual part of it. And that, by definition, makes it a heterogeneous mixture. Now, there is a curious mixture that has to do with the term emulsions. An emulsion is a mixture of immiscible liquids. Immiscible means it's not supposed to be able to mix together. So when you have two liquids mixed together that don't mix together, you have to have an emulsifier. That is something that kind of holds it together. It acts as an adhesive. Now, we're not going to inject glue into anything and call it an emulsifier. These just happen to work with the bonding of keeping these liquids at least bonding to it. And a perfect example is mayonnaise. Mayonnaise has an emulsifier. That mixture is considered an emulsion. The emulsifier in mayonnaise is eggs. The eggs are what keep the other particles together, I guess would be the way to do it. It's the emulsifier. It holds the emulsion together. Same thing is true for cream. There is a protein in cream that serves the same purpose. It is an emulsifier. let's talk a little bit about another page here. Let's go to this one. We'll talk a little bit about homogeneous mixtures. Homogeneous mixtures, you see we have a few terms here also: solution, solute, and solvent. And I have a couple of different things which can show you that the solute is what is mixed into the solvent. The solvent is like the water and the solute is like the sugar. The thing you mix in is the solute. And here's a pretty good way of looking at it. Here's the little bitty particles that are mixed in is the solute, and the thing itself is the solvent. And of course, what it produces is the solution. If each substance, well, if you have a salt-water mixture, the salt is the solute, the solvent is the water. Now, if you have miscible liquids, now these are liquids that can mix. These miscible liquids are sometimes hard to separate. And if you have these miscible liquids, there are sometimes some ways you can separate them depending on their boiling point. Say you have a liquid here that is a mixture of 2 or 3 substances. Just to make it simple, we'll make it 2 different substances that are mixed together here. If one of these substances has a different boiling point than another, you can separate them by distillation. Here's an example of distillation. You put the solution here and you heat it until it gets to the point where one of them evaporates. That's why having 2 different boiling points, you would be able to separate it. 2 different boiling points means liquid A would evaporate and be able to trickle down here, and they have the cold water here which would kind of help the process, and you would end up with just liquid A here, and liquid B would be left here. Now, if they are of similar boiling points, there is another way in which you can separate them, but we're not going to go over that one here. Let's go to another slide, Clyde. Ways a solvent can dissolve faster. If you have, say, tea here, you know that there you can put varying degrees of sugar into the tea. You can put a small amount, it not be near as much in it. You can put a lot amount and have it really sweet. And if you wanted to dissolve it faster, you probably wouldn't have all this ice in here, because one way is to have a hot solvent. If the solvent, the water, is hot, then that makes it easier for something to dissolve. So a hot solvent is one way. Another way is if the solute is broken into many pieces. For example, if you were to have just a sugar cube, and drop it in the bottom here, even if you had several sugar cubes and started stirring it up a lot, it would not dissolve as fast as if you had the sprinkled sugar on it. If it is broken up, solute broken up, then it just dissolves faster. And a third way you would have things dissolving faster is by stirring or shaking the solution. Stirring, shaking. Yeah, if you were to just put the sugar down at the bottom here, it eventually would dissolve in, but if you stir it up, then that's how you get it dissolved in. I have a term here called the universal solvent. The universal solvent, well, we've got a lot of it here on Earth. It's water. And when you think of solutions, you often have water that is the solvent. That's just how it's going to end up being. Now, I have a water molecule right here. Now, the characteristics of a water molecule make it more likely to be a solvent. And what the characteristic is that it's polar. It is a polar molecule. I think we may have discussed this earlier. The oxygen side has a partial negative charge. You know, 2 hydrogen, 1 oxygen. And that means the hydrogen side has a partial positive charge, the cation side of the periodic table. So when you have ionic bonds like NaCl, you may remember they're not true bonds, they're just the ions pushed together. And you have something that is positive like Na, it is attracted to the negative side, and the negative Cl is attracted to the positive side, so it's just more attracted to water itself because it's polar. Now that kind of brings up a point. Would a non-polar compound be willing to dissolve itself in water? Usually not, because kind of the rule like dissolves like means that polar solvents usually dissolve in polar solutes usually dissolve in polar solvents, and nonpolar solutes dissolve in nonpolar solvents. This is the like dissolves like rule. Let's go to this next page. We have several things that I didn't get to yet. Concentration, dilute, and concentrated. The term concentrated is the amount of solute in a given solution. If something is considered dilute, you have a small amount of solute. If something is considered concentrated, you have a high amount of solute. Talking about solute here, the things that go into the solution, to the solvent. Small amount it is dilute, large amount it is concentrated. That is part of the concentration. I guess you can say that both of these are kind of underneath the term concentration. Now I can go to this back page. A solution that is unsaturated is a solution that can dissolve more solute. If this tea here can get more sugar into it, then it is unsaturated. So if you don't put much into it, it's unsaturated. But we all know that you can put just as much sugar as you can into tea. And at that point where you cannot put any more under normal conditions, then it is considered saturated. Naturally, you'll find more unsaturated solutions than saturated solutions. Solubility. Oh, what would happen to sugar if you just put it in a saturated solution and stir it up? It would still stay at the bottom. There's just a point at which you can't get any more into it. A solubility is how much solvent can dissolve into how much solute can dissolve into particular solvent. You can actually measure how much sugar will go into this tea. Sure, there is a way you can have a supersaturated solution. That means you're actually getting more, in this case, sugar into the tea. The way you do that is to get it to the point of saturation and then you heat it up. You may remember one way to get things to dissolve faster is to heat up the solvent. So if you heat up the tea, you can actually put more sugar into it, and it will be something called supersaturated solution. It holds more solute because the temperature of the solvent was increased, so you can get more solute in the solution. Now, solubility is usually measured at that point of saturation, and you have a percentage called molarity, and this is usually a percentage, and it's the moles of solute, that's the amount of solute, over the amount of solution. So if you have a lot of sugar, then you have a higher molarity. If you have a little bit of sugar, you have a smaller molarity. Okay. I know we've had to digest, no pun intended, a lot of tea and information here. Go ahead and go back to the questions. I hope you learned a little bit. And hey, don't forget to read about this in your science book.